Students, hi, this is Mr. Bob, and this is a video on vector components and SOHCAHTOA. And before watching this video, you should make sure you have focus notes set up on your paper. Remember, you can use a digital version of it at bit.ly/F, template, or you can just do it on your own paper. And have a colored pencil or a highlighter ready. I think that would be helpful as well. So some things to think about when you watch this video: please avoid mindlessly copying. If you need to, stop and pause the video and rewind. You can also watch it at more than 1x speed if that works for you. Make sure you actively listen and write, selectively write what stands out to you, and feel free to use abbreviations as you see fit. When I give you a sample problem, I strongly recommend you pause the video and try and work it as much as you can by yourself. Make your brain struggle and think for a while first, and then resume the video and see their answer and compare it to yours. And if you're still confused by the end of the video, please mark your notes on those spots with points of confusion, and make sure you make a mental note or jot down somewhere to follow up with a classmate or with me. So we have two learning targets for today, and they are: given a vector at an angle, I can basically figure out the horizontal and vertical components using trigonometry. And then given the components of a vector, I can find the resultant vector. So let's get right into it. Suppose we have a ball. I'm going to start with a scenario here. Suppose we have a ball that's moving simultaneously in the X and Y direction. And let me do one thing here really quickly. Yeah, we'll move it over here. And a diagonal as shown. So you can see there, you've got this ball that starts out, and I'm starting it at the origin of my coordinate system. And notice what happens here. Whoa, did you see that special effects? Let's see that one more time. Notice what happened here. So the red ball is the one that's actually moving, but what I did is I created versions of the ball moving, or shadows of the ball moving just in the Y direction and also just in the X direction. And if you notice, they have velocities as well, right, as they move along. And hopefully you can notice that the shadow of the ball moving horizontally is moving a little faster than the shadow of the ball moving vertically. Okay, so what I'm trying to get at here is this idea of resolving a vector into its components. And to do that, we're going to do the following. So one way we could do it, obviously, is if we had a meter stick or a measuring tape, we could get it out and kind of look at what's going on here. We could look at the distances traveled, okay? But there are more sophisticated ways to do that. Okay, and we're going to talk about that here. But notice, to get to that sophisticated way, I just want to point out something to you. Notice you have that 9 meter side here on the vertical. Watch what we can do with that. We can move that over here to the right. And notice what we have here outlined in the dotted orange is a right triangle. Okay, and that's important because we can apply some math that you've learned, that you've been exposed to that right triangle to help us out here in the physical realm. The key point that I want to make in this slide is that vectors at an angle can be broken down into pieces. We call them components. It's just a fancy way of saying a piece that is represented by shadows. Okay, so let's say we have a vector A and it's at an angle like you'd see there. What can I talk about it? How can I talk about it? I can break that vector down into what we call horizontal X and vertical Y components. And I can label the horizontal component A sub X, as you can see there in blue, and the Y component A sub Y, as you can see there. And furthermore, obviously, like I showed you earlier, that A sub Y also applies over to the right, because remember, vectors can be moved around as long as I keep the length the same and the direction they're headed the same. So I've got the horizontal and the vertical component. If I had a protractor, I could actually measure that angle. And just remember, you probably know from math, theta is a symbol we often use for angles. That's the Greek letter theta. And the final thing, just to kind of review from math, is that if we have a right triangle, what is the relationship between the length of the sides? Well, you may have remembered something like a squared plus b squared equals c squared, but in this triangle, the way we've annotated our sides, it would be that a sub x squared, or the horizontal component squared, plus the vertical component squared, is going to equal the magnitude of the hypotenuse squared, a squared. All right, so here's where we get into the real nitty-gritty, and we go back to talk about some trigonometry, which you may or may not have been exposed to. I suspect most of you have at least been exposed to this to varying degrees. So this is really important, and it's going to be important for us for pretty much the rest of the year. if you think about it, this wonderful thing about math is that what we've discovered a long time ago is that if I have a right triangle there, or if I have any triangle, but let's just call that a right triangle right now, there's a special, the ratio between the length of the sides is constant regardless of how big or small the triangle is, as long as it has the same angle, okay? So in other words, we have these three ratios, these trigonometric ratios that we know to be constant if we just know the size of this angle here. And so for this given angle theta, I have three trigonometric ratios I can define. One is sine, the other is cosine, and the third one is tangent. And let's define each. The sine of an angle is defined as the ratio between the length of the opposite side, in other words, the side that's opposite the angle, and divided by the length of the hypotenuse. So it's opposite over hypotenuse. The cosine of an angle is measured to be the ratio of the length of the adjacent side. The side adjacent is another word for next to. So that's the side of the right triangle that's next to the angle. Again, divided by the hypotenuse. And then finally, the tangent of an angle. The tangent of an angle is defined as that ratio between the length of the side opposite the angle divided by the length of the side adjacent the angle. Opposite over adjacent. So we have sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. If you think about it, that creates a very nice mnemonic that I learned when I was in high school, and I don't know for how long it's been taught, I suspect for a very long time, SOHCAHTOA, okay? And this is an important mnemonic that you do want to remember because it's not something I will give to you on exam. I expect you to know it, IB expects you to know it, so that you know that if you're trying to find the sine of the angle or whatever the case may be, you know which of the sides it corresponds to. So let's do an example problem here, and let's see what happens with this example problem. Let me just move some things around quickly. Perfect. Okay, I've got a marble and it's launched. It says at a velocity of 12 meters per second at an angle of 30 degrees above the horizontal. And the question is at the start, how fast is it moving horizontally and vertically? So I'm always going to start out with a drawing. And this is really important here. So notice, here's my vector, and I'm going to call it v sub I, because that's my initial velocity, right? And my angle I know is 30 degrees. So I can draw that in like that. And so if I want to know how fast it's moving horizontally, that means I'm going to have to figure out the x component. So I'm looking for, one of the things I'm looking for is vi in the x direction. And then the other part I'm going to be looking for is the initial velocity in the vertical direction. I can draw that like this, VIY. Awesome. Okay, so now let's apply our trigonometry to figure out first the horizontal. So horizontal, let's see what I want to do here. If I think about it, what I want to do is I want to, now let's get another highlighting color. Highlighter, yep. What color do I want the highlight to be? Do I have a choice? I'm not sure I do. Okay, so if I want to know what the length of this side is. So I have to pair that with two things I already know. Well, I already know the angle, and I already know that the length of the hypotenuse, v sub I, is 12 meters per second, right? So I know the hypotenuse, and I need to know the adjacent, right? Because that's next to the angle. So that's v sub ix is next to the angle. So with that in mind, which of these is going to work? Is it going to be sine, cosine, or tangent? Notice cosine is the only one that correlates the adjacent and the hypotenuse. So indeed, it's going to be cosine. And so let me just make sure I get this right here. Hold on. Come on. There we go. Come on up. I want the pen back. There we go. Awesome. So what I'm going to say here is that the cosine, this is kind of funny. I got to change the color. Okay. The cosine of 30 degrees is adjacent being, in this case, VIX, divided by the hypotenuse, which is V sub I. Okay, now what can I do? I just want to solve for VIX. So to do that, what I'm just going to do is I'm going to multiply both sides of the equation by what's on the denominator, which is VI. And when I do that, the result I get, these cancel, and I get that VI, whoops, nope, don't want the joke yet. VI VI cosine 30 degrees equals VIX. And I can substitute in here 12 meters per second for VI and multiply that by the cosine of 30. And I'll get my initial velocity in the x direction. Let me just do that really quickly on my calculator. 12 times cosine 30. By the way, you want to make sure you're in degrees. And when you do that, VIX equals 10.4 meters per second. Okay, so I have figured out that's how fast it was moving horizontally at the start. What about vertically? Well, vertically is VIY. So that's over here. Do I dare even try that? VIY, okay. So I have VIY this time. So what trig function is going to work best for me? Well, now that I've solved the one side, I could use any of these. But if I'd solved for the vertical first, I would have had to go with sine, because notice I'm trying to find the length of the side opposite the angle. So I'd have to have opposite, and I already know hypotenuse. So I would say the sine of 30 degrees equals, opposite is VIY, hypotenuse is VI. And so again, I want to, there we go. Okay, this is just not working out like I'd like it to be, but we'll get through it. To solve that, I'm going to multiply both sides by VI so that that cancels because I'm solving for the vertical component. And so I get that VI sine 30 equals VIY. So that would be 12 meters per second. The sine of 30 is one of those convenient ones. It's 1/2 equals VIY. So 6.0 meters per second equals VIY. So I know that when that marble was launched at a velocity of 12 meters per second at that angle, initially it was moving 10.4 meters per second horizontally and 6.0 meters per second. Okay, we got through that. Time for a joke. Did you hear about the mountain climbers that contracted coronavirus but couldn't infect others? You know, you as physics students should know that because I've told you very early in the year that scalars are not vectors. Ha 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 ha. Okay, we have to have a little bit of humor even during a pandemic. So keep that in mind. All right, last example. This example, Lily walks 45 meters on a staircase that rises at a 36-degree angle with respect to the horizontal x-axis. Find the x and y components of her journey. Well, again, let's do a little drawing here. This time I've made it ahead of time. Notice in green there is the 45 meters. Lily's walked up the staircase. And notice I've drawn the angle and I've drawn the x component and the y component. A sub x, a sub y. So again, need to figure out SOHCAHTOA. So I'm just going to write that up here as a reference. SOHCAHTOA. All right. So let's first find the y component, okay, just to kind of do something different. So y component. So the y component is opposite the angle, right? And so I want to know what this is. That's what I'm looking for. I know what the hypotenuse is and I know what the angle is. So opposite hypotenuse looks like I'd have to use sine. Indeed, I would say sine of 36 degrees equals a sub y over a. Okay, and once again, I just want to be very clear and transparent about what I'm doing here. I'm solving for a sub y, so I have to multiply both sides by a. The a's cancel, and I'm left with the result that a sine of 36 degrees equals the y component. The a I know to be 45 meters. I'm going to multiply that by the sine of 36, and that's going to give me my answer. And I get 26.5 meters equals a sub y. I will acknowledge to those of you who are wondering, I'm not being a stickler on sig figs, so just don't worry about it. Okay, and then the x component. So for the x component, what side is this relative to this angle? This is the adjacent side. So we have adjacent. And you know what, just for Well, let's just stick with what we're doing. Adjacent hypotenuse, okay, adjacent hypotenuse, so that would be cosine. So we would say cosine of 36 degrees equals a sub x over a. So again, multiply both sides by a. By the way, after a while, you'll get to realize that, oh, if I'm doing cosine on these types of problems, it's always, if I'm doing the horizontal components, cosine, if I'm doing the vertical components, sine. That'll work for a while. It gets trickier though when you get to angled ramps, when we talk about that and we're talking about forces. So just realize that it won't always work, but it can be something, it can be a shortcut that you use for this. So 45 meters cosine 36 equals a sub x. Do that quickly in my calculator. And I get that, what was that? Oh, it just disappeared. That the x component, how far Lily walked horizontally was 36.4 meters. So again, couching it back in real life, Lily, in walking 45 meters at that angle, she actually walked 36.4 meters horizontally and 26.5 meters vertically, okay? So again, just terminology-wise, if you ever hear or see a request to resolve a vector, what that means is to break it down into its x and y components. And in doing this problem, we've resolved that vector into its x and y components. So hopefully you learned that given a vector at an angle, you can find the horizontal and vertical components. And if you give them the components of a vector, you can find its resultant vector. Thanks, everyone.